we have here two signals, H and X, and you want to take the convolution of these two signals. But at this time, instead of using the graphical representation, which is exactly what we did in lecture 2, we're going to use Laplace transform. So let me go to lecture 2. This is the solution we found in lecture 2. You see it's exactly the same. And the way we proceeded in lecture 2 was to do the graphical approach, which required, excuse me, that's here it is, which required taking one of the signals, flipping that over the tau axis, adding a time delay t, and then shift the time delay, look for overlaps, do the integration, and then come up with one expression that is a discontinuous function because it's now defined in different regions of the time axis, and the part in red here was the solution we found. So this was relatively long. Let's instead use the Laplace transform in this lecture to do the same problem and see if we come to the same solution. So these are the two functions we have, and let's use Laplace transform to do them. So what we are actually looking for is a property in the table of Laplace transform that would allow us to use the convolution of the signals, to take the Laplace transform of the convolution of the signals, and hopefully that will make the process of finding the convolution easier. And here we have a property number 33. So take your table of Laplace transform with you. We are going to use that throughout the lecture today. And this property here says that the Laplace transform of the convolution integral is simply the multiplication of the Laplace transform of each function in the Laplace domain. So let me write this on the board. We are doing the convolution of h of tau x of t minus tau d tau. Right there. And you're taking, this is what we want to compute, but we could then take the Laplace transform of this, which is the same as h of s times x of s. The reason I'm going back here is that later we have an exercise where we're going to use the same principle to find time response of a mechanical system. Now, this is a lot easier because all I have to do is to take the Laplace transform of these two signals, right? And then multiply them and find the inverse. And the inverse then would be the convolution of them. We have an exponential waveform decaying, and we have a square waveform. So this exponential decaying here could be, for example, the impulse response of any mechanical or electrical system. And h of t could be the voltage or force applied to it. So having the impulse response of the system x of t will allow us to compute the response of the system to any arbitrary input. So that's what we're going to focus on today. So here is the two signals we are dealing with. Now, to take the convolution of them, we need to take the Laplace transform of each signal and then multiply that. So this signal here was given as exponential of -3t. And this signal here is, we can find the Laplace transform of that. So what is x of s? If x of t is given here, what is x of s? Let's call this y of t. So this is y of t. So x of t is exponential of -3 times t. What is the Laplace transform of that? From the table of Laplace transform. Let's take the Laplace transform of that. So this is y of s, not y of t. So y of s is Laplace transform of x of t. What is that?
Is it e to the -3t minus e to the -5t?
We are talking about this one.
Oh,
right?
sorry, I'm looking at the wrong function. Sorry.
Yeah.
I was looking at the
right. We'll get there. Yeah. You're right about that one. Yeah.
Is it 1 over s plus 3?
1 over s plus 3. Very good. 1 over s plus 3. We can go to the table of Laplace transform, and that would be line the second option in the table. Right, second one there, exponential of at 1 minus as times minus a. Okay, so this is x of s. What is the Laplace transform of that one? This function is u of t minus 3 minus u of step t minus 5. When you take the Laplace transform of that, that becomes, this is a this step function. Yeah.
E to the minus 3t minus e to the minus 5t.
3s, right, is Laplace
Sorry,
now,
s, yeah.
minus exponential of minus 5s. Something is missing. What's missing? These are the time delays, right? The time delays, the exponential negative ts and 5s. What is missing? We are missing the step function, right? So this is the time delay applied to the step function. But we also need to take the Laplace transform of the step function itself. And what is the Laplace transform of the step function? Is 1 over s. So that's all divided by s.
I'm just a little confused. Is ys? What are we doing the x? Are we doing the Laplace of the graph on the left, or not the graph? This the step function of the left or the right one?
This is step function here. Is this a step function?
Okay,
right there.
Thank you.
Right. This is not a step function. This is the exponential negative 3 at t. All right. So this is h of s, and this is x of s. Are we good here? Is it clear why there is 1 over s here?
No, sorry, can you just repeat why it's 1 over s, please?
Right. So let's do, what is the Laplace transform of u of t? Is 1 over s. Right? If you now time shift by a seconds, we time shift the output by the Laplace transform by adding this component. Right? If you had a function, let's say sine of t minus 3, what would be the Laplace transform of this? It would be the Laplace transform of the sine wave, which in this case is 3 over s squared plus 9. That's the Laplace transform of sine of 3t delayed in time times that.
I see, that makes sense, thank you.
I had a question about the left graph.
Yeah.
So why are we doing just x of t equals e to the negative 3t? Like, why are we not looking at the step function as well with that?
The step function is here.
Just the equation on the slide, it's
For this one.
Yeah,
Yeah.
e to the negative 3t times u of t.
Okay, good question. So why are we neglecting this? This is actually times u of t. So this means that when you define the function only exists for positive values of t. For negative values of t, that's 0. So when you do the Laplace transform of that for a function that is only defined for time positive, the greater than 0, then integration goes from 0 to infinity of f of t exponential of negative st dt. So this is not negative infinity, becomes 0. So we can neglect that because the definition of the Laplace transform for time greater than 0 only starts at 0. Okay, so with this in mind, this becomes 1 over s plus 3. And the step can be neglected because of the limits of the integration. You can verify this by just computing the integral here, and it will give you that result. It's not intuitive at all, but that's a property of the Laplace transform. So for now, let's to simplify the problem, let's assume that our function is simply defined like that. This is more of a mathematical detail, but that's a very good question. I was actually hoping that nobody would notice that because it is not intuitive at all. Okay, but the function being defined for time greater than 0, the limits of the Laplace transform will change. And if you do this calculation, we'll find the what I found, the same result. Okay. Does that
Thank you.
partially answer it? Yeah. Okay. This is the equation we have now. Are we good? That's y of s, which is y of t would be the convolution. Y of s is the Laplace transform of the convolution. Any questions? No? All right. So we can expand this. If I hear no questions, I'll just keep going. All right. So we can now multiply s there, and then you have exponential number 3s, negative 5s. What do we do next? Now we want to find the inverse of this. How do we find the inverse of that? We know what to do with these terms. They look very intimidating, but they are actually just adding a time shift. We'll deal with them later. So let's focus here. What do we do now? How do we find the inverse Laplace transform of this? It won't be in the table. You won't find this structure in the table. So what do we do?
Partial fractions.
Partial fractions. Excellent. And this partial fraction will be written as, in which form? We have two first order polynomials. So we simply need a over s plus b over s plus 3. Let me call this polynomial here. Let me call this p for partial fraction. Then this one doesn't need to be included for now. It's called that p, and then it's called this p of s. So we want this to be equal to that. Should I go through the steps to calculate a and b, or are we okay with that?
Could you go over the steps?
All right. So how do I find a? A is p of s, which is this function, or this function. All right, now let's look at this function here, times whatever divides a, which is s, so times s. And this is evaluated at the value of the denominator, when the value of s that makes the denominator 0. So this would be s equals to 0. So this gives 1 over, so p of s is that, times s, this s and that s cancel out. So we have s plus 3 evaluated at 0, which is 1/3. Tell me the equation for b. B is p of s, which is this, times what? Whatever divides b, which is s plus 3. And this is evaluated at whatever value of s makes the denominator here 0, which is s equals to -3. So this gives, if you multiply this by s plus 3, we are left with 1 over s. And when we evaluate this s minus 3, this gives negative 1/3. Okay. Questions? No?
Not a question, but could you stay on that slide for just a sec? Or
Sorry.
not slide, but keep the writing there.
Sorry, I didn't catch that.
Just wondering if you can keep the writing there for a second.
If I can keep.
like leave the writing, sorry.
Are we good? Yeah. Okay, so now y of s can be expanded using this. So y of s now becomes 1/3 of s. 1/3 here replaces a, so 1/s minus 1/s plus 3. I just factored out 1/3. Exponential of negative 3s minus exponential negative 5s. Okay, now we are ready to take the inverse Laplace. And the inverse Laplace of y of s is y of t. I will do the hard part here and you do the easy part. So the hard part is, what is the inverse Laplace of 1/3? That's 1/3. Now you do the easy part. What is the inverse Laplace of that? Well, what we can do is first take the inverse Laplace of these two terms and then time shift them with these two terms. Okay, so let's first do this multiplication here. We have 1/s. What is the Laplace transform of 1/s? The inverse Laplace transform. Let's go to the table. That is number 1. That's a step function. We're now in the frequency domain with 1/s. So when we go back to the time domain, this becomes 1. Or becomes the step function, because delayed by 3 seconds because of this time shift here. All right, so this was the time response of the Laplace transform of a step function, 1/s. But now this step function is delayed in time by 3 seconds because 1/s multiplies that. So this is a step function shifted in time by 3 seconds. And 1/s times the other one is the same, but now shifted by 5 seconds. Okay. Now we have another term here, and let's do that multiplication. Let me use a different color for that one. We have these two multiplications here. So what is the inverse Laplace of 1/s plus 3? Well, we did it here, right? It's the exponential of negative 3t. When you took the Laplace transform of that, we got this. So the inverse Laplace of negative 1/s plus 3 is negative exponential of negative 3t. But now this is multiplied by this time delay. And this time delay adds negative 3 seconds to time. So time that was t now becomes 3 minus t. And plus the other term, so negative times negative, positive exponential of negative 3t, but now t is time shifted by 5 seconds, t minus 5. These functions can only start when time reaches 3 and 5 seconds. So we need to multiply them by the time shift, so they only exist by the step function with a time shift, so that they only exist when time is greater than 3 seconds for this one and greater than 3 seconds for that one. Otherwise, these elements would also exist below for all times, all values of t, even negative values of t, and then they would not correspond to the input we have there. Are there any questions?
Yeah, this isn't really related to this question, but what would the Laplace be of the ramp function.
The Laplace of a ramp function. Yeah. So the ramp function increases linearly with time. So it would be something like y of t equals to a constant times time. Now I can go to the Laplace transform. That would be in the table. There would be number 3, which gives y of s as a times 1 over s squared. And that's Laplace transform of the ramp. Any other question? No? All right. So if there are no questions, let's go back to the result we found in lecture 2 here, and let's try to compare them. So you see what we found in this lecture, but in lecture, it was just one expression with all these step functions. But in lecture 2, we found something slightly different. We found something that is discontinuous because it has now different values for different portions of t. So let's see if what we found here is the same. Let me just make some room here in the whiteboard, and then we are gonna see if they match. All right. So here we identified 3 different regions: t smaller than 3, t between 3 and 5, and 3t greater than 5. Let's see how that helps this equation relates to that. So the first thing we can see in this equation is that we have 3 step functions all over. And if this step function, for example, is 0 for t is smaller than 3, because we have a negative value inside, and 3 is, and this function is 1 when t is greater than 3. So what happens if t is smaller than 0? If t is smaller than 0, actually, we can go all the way to 3, because if t is smaller than 3, then this step function is 0, this step function is 0, this is 0, and that's 0. Everything becomes 0, because all the result inside of these step function is 0. So for 3 smaller than 0, y of t is 0. What happens if t is between 3 and 5? Well, for 3 between 3 and 5, this step function is now 1, right? Because we passed 3 seconds. But this step function is 0 because we are below 5 seconds. So u of t minus 3 is 1, and u of t minus 5 is 0. So y of t simplifies to 1/3 of 1. This is 0. This one is exponential of negative 3t minus 3. All right, this is 1, and this is 0. All right, because of these two properties here. And the last part that we have to evaluate is what happens when t is greater than 5. And what happens when t is greater than 5? Well, that u of t minus 3 is 1, and u of t minus 5 is also 1. Now we can rewrite this expression using that. Just give me 1 second here. Make some room. So this is 1, this is 1, that's 1, that's 1. So here is 1 minus 1 is 0. Y of t is, this is 0, so 1/3 of 0, minus, this is 1, so minus exponential of negative 3t minus 3, plus exponential of negative 3t minus 5. Okay. Simplifies to that because that's 0. So this can be rewritten as 1/3 of negative exponential of negative 3t exponential of 9, right? Just multiplying these out, plus exponential of negative 3t plus exponential of 15, right? 3 times 5. We can now factor out exponential of negative 3t. So y of t is 1/3 of exponential of negative 3t times exponential of 15 minus exponential of 9. So here we have the first range, second range, third range. And if you go back to lecture 2, that's precisely what we found there using the graphical method.